Hi, let's talk about the normal force. So the normal force is kind of a foundational idea um, and something that's going to crop up a lot in problems involving Newton's laws. So let's take some time and talk today about what it is. So before we jump into the normal force, though, I want to talk about a couple definitions, and that is mass uh, versus weight. So these things are not the same. So mass does not equal weight. We tend to kind of talk about them as if they're the same thing, but they're not. So the mass of an object is its resistance to being accelerated. So, and in other words, it's a measure of an object's inertia. So when we talk about the acceleration of an object due to the net force applied to that object, it is inversely proportional to the mass. And this is a way of saying that the mass is resisting the motion, or resisting the acceleration, rather. The larger the mass, the harder it would be to accelerate the object. And this, of course, is Newton's second law. This is to be distinguished from weight. So weight is the force of gravity on an object. So the force of gravity. Um, so mass you can't really change. It's a characteristic of the object. To change an object's mass, you'd have to do something to the object, remove material or something like that. So you can't. It's an immutable characteristic, more or less. Weight, on the other hand, you can change, and I should say we use different letters to indicate this. We might call this W, or the force of gravity, or usually we'll just talk about it as being mg. But you can change an object's weight because you can change gravity. Uh, and what I want you to think of as an example for that is, think of a moonwalk. If you think of a moonwalk, the gravity on the moon is, of course, much less than the gravity on the Earth, about a sixth. So the weight on the moon is also much less than the weight on Earth. Okay, so these, two important definitions to have uh, as we start to talk about the normal force. So let's talk about the normal force. Um, so we talked to originally introduced this in regards to Newton's third law. So if you have an object, let me give you an example. If you have an object, let's say you have a coffee cup that's sitting on a table. Um, the coffee cup is going to have some weight. It's pointing down. Try and be good about having a coordinate system in our picture. There is going to be that object's weight is acting on the table, pushing down. So let me just write it like that. There is going to be an equal and opposite force pushing back on the coffee cup, and that is the normal force. And when we talk about normal, what that is actually referring to is the fact that this force is perpendicular to the surface. So, and we can also approach this as an application of Newton's second law. If we sum the forces in the y direction, notice the only thing that we're caring about is the y direction. And we're talking about on the cup. We sum the forces on the cup. The normal force will be positive. The force of gravity will be negative. It's pointing down. And this is going to equal the mass times the acceleration. Now, in this case, that equals 0. The object is not accelerating because it is at rest on the table or wherever it's sitting. So this would be an example of where, if you then solve this, you would find that the normal force is equal to the weight of the object. It's equal in magnitude, but it is, in this case, it's in the positive y direction. And if we're being careful, we would indicate this direction with a unit vector, j hat. Okay, and we'll talk more about our vectors and keeping track of proper directions of things as we go forward. So let me give you another example for the normal force. So the next example that I want to give you is to let's actually calculate an example. So let's do something that not just with variables, but with numbers. So suppose you have some mass that equals 20 kilograms. And let's figure out what the magnitude of, let's figure out what the normal force is. Okay, so we'll give ourselves a coordinate system. Oops. We will give ourselves a free body diagram, so we know the object's weight is pointing down. The normal force would be pointing up. We do, again, our sum of forces. So to be real explicit, just like the example above, the sum of forces in the x direction would be 0. There's no forces that are pointed along x. But the sum of the forces in the y direction, we would have the normal force minus the weight, and that is going to equal 0. Now, we can then solve this. This means that the normal force will equal mg. And we can put in our numbers. So this would equal the mass, 20 kilograms, times g, 9.8 meters per second squared. And when we multiply those things out, we would find that this is 196 newtons in the j hat direction, in the positive y direction. So, we could also note that the weight would be negative. Or if you want to think about this, you could think of this as being the same exact magnitude, but in the negative j hat direction. Because the weight is pointing down, the normal force is pointing up. Okay. Let's look at a little more complicated example. So now I want you to consider our 20 kilogram object. Actually, let me put the, oh yeah, we'll leave it like this. We're going to put an object on top of it. Let's say that one's 10 kilograms. So now I want to show you, or try and model to you, doing our free body diagrams. So this might seem kind of like, well, this is a simple example, but we want to start with simple examples, and then when you're analyzing more complex situations, this will be a useful skill to have, useful tool for you. So let's be pretty methodical. Let's call this object 1, this one object 2. So if we're looking at object 1, what do we have? We have the weight would be pointing down, m1g, and the normal force would be pointing up. This is the normal force. And actually, I'm going to say that this is 2 on 1 as well, just to kind of have some additional information there. And then let's also draw a free body diagram for our second object. So for this one, what all do we have? We have, for accounting the forces on the object, we have its weight. This would be m2g. We would have the normal force. Now that's, just to be really explicit, that's the table on 2. We would also have the weight of object 1 pushing down on object 2. And that would be the sum of the forces on, that would be the 3 forces that are acting on object 2. Okay, so the free body diagram, you're just accounting for the forces that are acting on the object. Okay, so then we can sum the forces. So let's apply Newton's second law, in other words. So let's look at object 1 first. So the sum of the forces in x is 0. There's nothing happening in x. The sum of the forces in y, we would have the normal force. This is 2 on 1 minus m1g. And this would equal the mass of 1 times its acceleration, but it's not accelerating, so this will equal 0. So in other words, we could solve this then for the normal force. 2 on 1 will equal m1g. And we could come up with a numerical value for this as well. So this is 10 kilograms times 9.8 meters per second squared. This will equal 98 newtons. Okay. So, and then for object 2, it's a similar story. The sum of the forces in x will be 0. We have no x forces. In y, though, sum of the forces in y, what will we have? We'll have the normal force. This is the table on 2. And then we would have minus m2g, which is pointing down, and minus m1g, which is also pointing down. And we can then, of course, this would equal the mass of 2 times its acceleration. But this object is just sitting on the table. It's not accelerating, so this would be 0. So then we could see that Fn, we could solve for Fn, the normal force, and we'll just say table on 2, would equal m2g plus m1g. Maybe we could simplify this and pull out a factor of g. And this is kind of what we would expect intuitively, right? The normal force is going to have to push up both against the force of the weight of object 2, but also the force, the weight of object 1. So this would be an example where the normal force, so in here we can come up with a numerical value. So it'll be g times 20 kilograms plus 10 kilograms. And so this would be, about 300 newtons. This is an example where the normal force does not equal the object's weight. So why I'm showing you this is because the normal force in this case does not equal the weight. But it is the same situation where, this is this perpendicular force that keeps the object from moving. Or I should say force that's perpendicular to the surface. Try and emphasize that. Okay, so that's an example where the normal force in this situation is actually larger than the weight. Let's look at a similar but slightly different variation of this. So the example that I want you to consider now is, what about this? So let me see if I can draw this reasonably well. So suppose you have your 20 kilogram object again. And imagine we have a cord, some pulleys, 10 kilogram object over here. Now, let's note our, let's call this, how about we call this one object 1, object 2. This will give us an opportunity to do our free body diagrams. So for object 1, what do we have? We have the weight, and that would be m1g. Well, let's see, did I do, actually, let me switch these around so that they're the same as what we did above. So we'll make this one object 2 and this one object 1. So we can look at object 1 first. So in this case, what do we have? We have the mass of 1 times gravity. We have its weight pointing down. Oops, I forgot my coordinate system. And then in addition to that, you would have, often use to describe a force in like a rope or a cord or something, we have a force of tension that's pointing up. Or you might use, just the letter T to represent tension. So that's the free body. Those are the forces that are on object 1, its weight, and this tension force pointing up. Let's look at object 2. So in this case, we have object 2's weight pointing down. We would have the normal force perpendicular to the surface, pointing up. And then we have one other force, so we also have this force of tension that's pointing up. Okay, so we have a picture. We have our free body diagrams. Let's look at Newton's second law for each of these situations. So for object 1, we'll be kind of methodical about it. There's nothing happening in x, so the sum of the forces in the x direction is 0. In y, however, we have the tension force pointing up, and so it's positive. And then we have minus m1g pointing down, the weight. That would equal m1 times its acceleration, but it's not accelerating, so this is 0. This allows us to solve for what that tension force is in terms of the weight. So we know the tension force is m1g. Now, from object 2, similarly, the forces in x are 0. The forces in y, however, we have tension force, positive, pointed up. The normal force, also positive. And the object's weight, pointed down, negative. This is going to equal m2 times its acceleration. It's not accelerating, though. It's just resting on the table, so this would be 0. So then we can solve this expression for the normal force. So we would have m2g minus the tension force. Notice then we can substitute in our tension force from looking at the other object and come up with an expression for the normal force that does not depend on the tension. This will be m2g minus m1g. And we can, pull out that factor of g. And, notice we could evaluate this. We're using the same combination of masses. So instead of adding them together, as in the example above, this would become g times 20 minus 10. So this would be, 98 newtons. And so this is an example of where the normal force does not equal the weight. And in fact, in this case, the normal force is less than the weight. And so in this situation, we're pulling up on the object, so the normal force would be less. And as opposed to here, where we were pushing down on the object because we have another object on top of it, and so the normal force is larger. So I think, I hope this kind of drives home for you some different situations involving the normal force. It's this force that's perpendicular to a surface. And where we're headed next is we're getting into more exciting territory where no longer are the sum of forces going to equal 0. So in other words, we'll see how things accelerate. So that's next. And one thing that I should have mentioned, these forces, just while I'm thinking of it, these are this normal force in the pictures that we have is pointed in the j hat direction. So this is j hat. This is j hat. Just a detail. We'll try and be sticklers about that.